Welcome to the CAE Associates webinar on nCode. nCode is a fatigue analysis tool now available in ANSYS. In this seminar, I will present a brief overview of fatigue and explain the traditional methods of performing fatigue analysis. I will then briefly discuss nCode's fatigue analysis capabilities and finally perform a demonstration of nCode. Fatigue is the initiation and growth of cracks. Usually they start from a defect in the structural part, and based on the application of cyclic loading, these cracks will grow to failure. The issue with fatigue is that typically the loads are much lower than would cause failure from a static sense. So you can have very small loads applied in a cyclic sense. These will grow cracks to failure, and typically you'll get very little warning when a fatigue failure will occur. So thus, prediction of life using fatigue is very important for any engineering product. Some basics about fatigue. When we talk about a fatigue load, just some terminology before we get started with any kind of demo, is you'll hear terms about the mean stress and the amplitude of the cyclic stress. The mean stress, shown on the figure here, is the average stress, and the amplitude is the difference between the max or the min and the average. So fatigue life is obviously dependent on the range, the stress, the maximum stress to the minimum stress, but it also can be highly dependent on the mean stress that's applied as well. Now, when we typically perform fatigue analyses, we have to base that on some fatigue test data that's usually provided for many materials. And fatigue life curves, as shown here on the bottom right of this figure, are typically done by doing constant amplitude loading, typically at a mean stress of 0. So you're basically looking at a max to the min, which is minus the max, and with a mean of 0. And you just apply that load until you reach failure, and then it gets plotted on what's called an SN curve, which is shown below, where the failure stress is plotted based on the cycles of failure of the application of that load that will cause failure. And then that's done over and over at different stress levels. And a couple things you'll notice from the figure below is that usually there's a lot of scatter in the data. And secondly, you can have a situation where the SN curve will flatten out, and any stress below that value is considered infinite life. That's called the endurance limit. As far as performing fatigue analysis, there's typically two basic methods of doing that. The first is we don't really consider the crack itself. We just use SN data, and we basically look to see what cyclic load will cause failure based on some SN data that we've provided, and then at that point we say that we've predicted the life, and that is really called crack formation. A second type of fatigue analysis is based on crack growth. That says that we do have a crack, and we know where the crack is located and what the length is, and then we can determine, based on crack growth laws and the applied loading, how many more cycles of loading we have before this crack will propagate to failure. The choice of that analysis is based on what you're doing with your analysis. For example, crack formation is usually done in the design phase or when you're just performing general fatigue analysis. Crack growth is normally done for in-service life prediction when there's inspections and we see that we have a crack and we want to determine the remaining life of the part. nCode is basically a crack formation analysis. It is based on SN data, the stresses to cycles to failure, and that is what nCode will do. Now, because of that, what you're essentially saying is you're going to first perform finite element analysis without any cracks in the model. So you will just be performing and getting and obtaining stresses and strains and displacements for an uncracked body, and you'll be feeding that result to ENCODE along with some type of fatigue data, and based on fatigue loading and SN data, and based on all that, you can calculate what the life is. You can perform basic just lookups in SN data plots, but as I'll describe shortly, in the fatigue analysis, it's usually much more complex than just a simple S-min to S-max cyclic loading. These complications that I'll be referring to are due to the fact that when we look at simple fatigue analysis and fatigue data and fatigue testing, the test data is typically fully reversed, meaning going from a stress value from plus to minus so that the mean is 0. We're talking about a uniaxial loading, so loading just in one direction. And typically, we're going to see also that there is always a large amount of scatter in all the data. And finally, the loading, even though fatigue loading is typically lower than the load that would cause failure, you can have local regions that may have plasticity occur in them, such as notches, and these locations will obviously change and alter the predicted life. ENCODE has techniques to address all of these complications, since in the real world we know that most of these things are not true or are different than what we're assuming in an analysis. ENCODE offers an advanced set of finite fatigue analysis capabilities. ANSYS has partnered with the ENCODE DesignLife analysis to be able to predict fatigue life based on ANSYS results. And note that ENCODE can run within the workbench environment of ANSYS, or it can also run standalone. And in addition to just ANSYS results files, it can really read in a large variety of different finite element code results files, which is what it really needs as a starting point. ENCODE is the leading developer of fatigue analysis software in the world, so it's a very mature approach to fatigue analysis, and it has a lot of easy-to-use yet very complex features to it, which I'll be demonstrating shortly. ENCODE also provides a significant material library that comes along with the code so that you can go ahead and bring in and go from their library all of the SN-type data that's required. In addition, you can, of course, always edit any of these or even bring in your own test data. I'm going to quickly talk about some of the main features of ENCODE, and especially pointing towards the complications that I've mentioned earlier. And these are listed here. I'm going to go through each one of these very briefly, just so to give an idea of the types of complications and procedures and complexities of finite element or fatigue analysis. First thing is the type of data. There's really two approaches to fatigue analysis concerning the SN data. There is stress life and there is strain life curves. Stress life curves are essentially for high cycle fatigue, and what they do is they assume that we have a very low loading, no plasticity, and the cycles are going to be very, very high in the millions, typically in the millions of cycles. Strain life includes that you could have material yielding and plasticity occurring in your model. It's typically more appropriate for low cycle fatigue. As you see in the SN curve below, the elastic line curve is the black straight line, and the plastic life line is the green line. The green really represents strain life. The black represents stress life, and the red line is basically a combination of both. And one of the things is that if you consider strain life curves, strain life essentially combines both the strain life and stress life data, so it typically can handle the entire range. Stress life will really just be considering the high cycle region. nCode can handle both stress and strain life data. Material fatigue curves, as I mentioned earlier, are typically constant amplitude, uniaxial sinusoidal loading, typically with a mean stress of 0, so it's fully reversed, as shown basically in the first plot there. But as we know, real loading in our engineering products can be very different than just a simple uniaxial, fully reversed load. For example, we can have different cycles with different mean stresses and different amplitudes, or we could even have something like on the bottom chart where we have a much more random type of loading where if we are measuring our loading over a certain amount of time, you'll get a much more realistic type loading. Regardless of how the loading is or how we define our loading, we need to deliver to nCode and to the fatigue analysis a description of how many cycles and what the range and the mean stress are for each one of these cycles. So if you only have data like in that third plot that I showed you that's a little more complex, nCode will use what's called rainflow cycle counting. Rainflow cycle counting is when it basically looks at your complex load, and the approach here is you imagine that the signal is filled with water, as shown in this third graph here. And what you do is you start by draining the water at the lowest valley. You look at that, and in that case we have one cycle that has a range of 450 and a mean of 225. And then we now have described that, basically the largest cycle, as part of this complex loading. And now we're left with these other three. So if we look at the next one at the bottom, that has a range of 50 and a mean of 150, and that happens once. So we record that as part of the rainflow cycle counting. And finally, we're left with those two final cycles, both of which have a range of 100 and a mean of 300, and obviously that happens twice. And rainflow cycle counting will automatically go through any complex load and provide nCode with the definition of a more organized type of loading, cyclic loading, that it can then use in the analysis. Another issue is if we have different blocks of loading, so we have different amplitudes here, shown on the slide of 3 different amplitudes, and we want to include the effect of those 3, we have to be able to include the damage from each one of those loads and then somehow combine those. And that's done with what's called Miner's rule of damage accumulation. Miner's rule is nothing more than we take the damage due to that load divided by the life, the total number of cycles to failure at that load. We sum those up for each of the blocks of loading, and if that is equal to or greater than 1, the part is failed. If it's less than 1, the part isn't failed. This is a very simplistic approach. One thing to consider is that the order of loading has no effect at all. However, even though it's simplistic, it's still widely used in the fatigue world, and it's what nCode will do when you apply different cycles. I mentioned that you can have, especially for a strain life type of application, you can have a plasticity occurring, especially in local regions like notches. And there are a number of ways to account for that. The first way is you can actually perform a nonlinear material response in your finite element analysis and feed that into the strain life fatigue analysis calculation. But another approach is that you use a linear response. You don't include the plasticity in the finite element analysis, but when you feed it to nCode, nCode can use what's called an elastic plastic correction in these locations. An example is the Neuber approach. The Neuber approach assumes that the elastic strain energy near that notch is equal to the plastic strain energy. Therefore, if you know what the elastic response is, you can then get the equivalent plasticity response at that notch without having to run a full nonlinear plasticity analysis. And nCode has a number of different elastic plastic corrections approaches that can be used to include the effect of plasticity in local notch regions. As I mentioned earlier, the fatigue loadings, in many cases, the data uses a zero mean stress, which essentially says that you have a fully reversed load from plus sigma to minus sigma, so the mean is zero. But fatigue life is often influenced by this mean stress, and so if you have loads where the mean stress isn't zero, you have to take that into account. And again, if you don't have data for exactly your particular mean stress, there are methods that can be used to incorporate the effect of non-zero mean stress into your analysis. The supported methods in nCode are listed on this slide, and the example here is, and one of the common ones is the Goodman approach, which is shown here, where the R ratio, the value of R, is equal to the minimum amplitude or the minimum stress divided by the max stress. So an R ratio of -1 would be a fully reversed load because the minimum would be the negative of the maximum. Finally, a few other quick items just to show the complexity and the capabilities of nCode is if you have a very complex load, cyclic load that you want to use and that comes into nCode, you understand that could be a very complex analysis with a very complex loading. nCode has the ability to compress the loading to try to get the main features of that loading without having to run every single small and individual cycle that you have here. There are several different ways to do time history compression. There's a peak valley method, a limits method. Each of these is going to try to simplify the loading so that the fatigue analysis can be done efficiently and still accurately without having to use every single step. Finally, as I mentioned before, most fatigue data is assumed to be uniaxial in nature, but as we know, our stress fields in our critical regions can often be multiaxial, and therefore we have to include the effect of the full stress tensor, not just the stress in one direction. And again, nCode has a number of ways to address multiaxial fatigue. There is the critical plane approach, where it'll search through planes to find the most stressed plane that would cause fatigue to occur. There's also ways to condense the stress tensor down to a scalar signed stress variable. All of these features are available in nCode. One of the beauties of nCode is that even though it contains many complex and advanced capabilities, it is still a very easy code to use. So I'll be demoing this in another minute or two, but just a review of the code itself. The way nCode works, and which I'll be showing you, is that it uses what are called glyphs. Glyphs are basically these graphical boxes that you can drag on and create on the main window of nCode, and each one of these glyphs performs an individual engineering function. Some are just used to bring in and store the finite element results. Others are used to bring in your cyclic load data. Some are used to define your analysis properties. Some are used to look at the results. In any of these glyphs, once you bring them together, you connect them with what are called pipes. And the pipes will just pass the data from one glyph to another based, again, on what you're doing. You can design this entire flow, and that's what it's called in nCode, is the analysis flow. And you can, of course, save this process once you set it up in a .flow file, which can be used for later on for any other analysis, fatigue analysis that is similar. And all of these glyphs, by right-clicking on them, you can access properties of that glyph, so you can edit any of the input parameters or settings. For a typical fatigue analysis, you'll normally see something as you see here, and up in the upper left glyph is basically storing your finite element models and the results that come with it. So when you first run ANSYS, you can then bring in the results, and they'll appear, and then you can plot all your results, your finite element results, look at the model, make sure you know exactly what you have. You don't need to go back into ANSYS or Workbench to remember what you did. Everything's right there. At the bottom left, you could, for example, have a description of your cyclic loading from some test data. It doesn't have to be that complex, but if you have that, you have the ability to bring in that data. Both of these are piped into, in this case, it looks like a stress life analysis. And in that case there, you would define all your settings. You would map whatever loads you want to apply to your finite element model, whatever fatigue materials that you want to apply to different parts of your model. You would do it here by just right-clicking on the analysis and performing that mapping. And then finally, they get fed to results glyphs where you can plot the damage and the life as a function of position all over your model. One of the key aspects of when performing a fatigue analysis is that you need to specify what materials are going to be used, what fatigue analysis materials are going to be assigned to each part of your model, how you're going to assign and define the fatigue cyclic loading, and of course all your fatigue analysis settings. And those three things are done by right-clicking on top of the analysis glyph. As you see there, the analysis glyph, if you right-click and the menu pops up, you'll see that you can edit the material mapping, load mapping, and properties of this analysis. And I will be showing a little more detail on those during the demo. What types of loading can be applied when you're applying cyclic loading? Well, you can start with the simplest, which is a constant amplitude sinusoidal loading, and just you would basically just apply the load in the finite element analysis, and then you would go ahead and read that into ENCODE and just tell ENCODE that you're going to use that as a constant amplitude. You could, of course, scale it. Or you could read in time series, where you basically apply your load cases in the finite element analysis, but then you would bring in some time series. It could be a complex time series or test data that you're going to apply as your cyclic load. So you maybe would apply a unit load in ANSYS, and then you would tell it to assign how that load actually cycles by using the time series. If you have a transient dynamic analysis and you really want to use every single step of that transient analysis as to define your cyclic loading, you can do that with the time step approach. So you would apply a transient loading in Workbench, let's say, and then you would define your cyclic loading by just reading in all of those steps during that transient event. ENCODE also gives you the ability to build duty cycles, which allows you to combine various types of loading, so that let's say you have a part that you know that it goes through various cyclic loadings throughout a huge event. You're defining different parts of that event. You have the ability to do that. And finally, if you want to do vibration fatigue, you can run a harmonic finite element solution, feed that into ENCODE, and then you would define your PSD loading in ENCODE. So at this point, that completes the brief overview. I'd like to perform a simple demonstration to illustrate the use of ENCODE in fatigue analysis. Okay, to begin the ENCODE demo, what I've done is I've opened up a ANSYS Workbench project that has a simple model that we're going to perform a fatigue analysis on. But first, I want to point out that ENCODE can be run standalone. You can run it directly from the Start menu. You don't need to run it inside Workbench. However, there are several distinct advantages by running it within Workbench. One is that all the material properties come into the engineering data, and you can look at them, edit them, and select which ones you want to use from within the engineering data tab of Workbench. And so that's one really nice feature. Another nice feature that you'll see is you don't need to set up an analysis flow for nCode. If in Workbench you're going to tell it what type of fatigue analysis we're going to do, and it will automatically set up a default flow for you, which is really nice. And then I think the third advantage is that all of the analysis data that you get from both the finite element analysis and the fatigue analysis will get stored as part of the Workbench project. So you'll get the fatigue analysis right inside Workbench, as you'll see. So we are currently inside the engineering data, and what you'll notice is that on line 9 up here, if you look at your library, which you get to by clicking on the little icon with the books at the top, you'll see that if you have installed nCode and are licensed to use it, one of the libraries will be the nCode matmul library. And in the middle here, you'll see a listing of all the different material properties that are currently included. And I'm going to pick for this model a carbon steel SAE 1045 390 QT. And one of the nice features, again, in Workbench is that we can, by looking at this bottom part, we can see all of the normal material properties that are going to be used to perform the finite element analysis, the modulus and Poisson's ratio, density, and so on. In addition, though, we have our strain life parameters. And one of the nice things here is, notice that we're doing a strain life. You'll see on the right a plot of our strain life, our total strain life plot, which is in green. And again, just being clear here, the blue line is really the elastic or stress life, and the red line is the inelastic or strain life. And combined, by combining those, you get the green line, which represents our strain amplitude to failure, or SN curve. And notice that if we wanted to, we could make a copy of this. We could redefine any of these coefficients that make up this particular material property. So at this point, I am going to click on the little plus button here, and that will add it to my engineering data. So if I now click back to get back to engineering data, you'll now see that the carbon steel is now available with the fatigue property. So I'm going to return to my project, and of course I have to go and right-click and refresh my model. And as we're waiting for that to refresh, one of the things you'll see here is on the left-hand side in the toolbox, you'll see now that there are additional analysis systems that relate to nCode. And in our case, we're going to start off by performing a time series strain life analysis. So we will be using the nCode time series to go. So what we're going to eventually do is drag this onto the solution. But first, let's go into the model, and we are going to take a look at this very simple model. This model essentially represents a simple shaft, and we're going to apply 2 unit loads to it. We're applying a bending load and a torsion load. And we're making these unit loads because we just want to tell nCode what directions the loads are in and get a unit response to it. But then we are, what we'll be doing is we'll then multiply that by our time series that we'll read in separately from, let's say, test data that we have. So the first thing we need to do is go to that solid and change the default structural steel to the carbon steel that we applied. So we'll click on our one piece of geometry, our one solid geometry, and change the material assignment. At this point, I'll just show you the boundary conditions. There is our force, and there's just a moment. And at this point, we're not going to really worry much about the mesh. We're just going to immediately solve this so that we can get on to the fatigue analysis. So we'll just use the default mesh in this case. And we'll wait till this solves. It's a small problem, so it should solve very quickly. And what you'll see is we'll get the stresses due to a unit bending and unit torsion type loading. And at that point, we can plot the results. There is the bending load stresses, and there is the torsional load stresses. So at this point, we are going to go back to the Workbench project page, and I'm going to drag on an nCode EN, or StrainLife time series, over the solution to the static structural analysis. A couple things happen. One is we get a lightning bolt back here, so I am just going to right-click and say Update, and that should quickly update. And then over on nCode, I want to right-click and say Refresh, because now we want to refresh that. And at this point, we can double-click or say Edit on nCode, and it's going to open up the nCode interface. And again, you can immediately notice that a flow is already in there. You have the ability to perform your own analyses from scratch and create any flow that you'd like. All of these glyphs are movable, and you can, over the right side is where you can drag on any type of glyph that you're interested in onto the background here to define it. But one of the nice features of Workbench, it kind of has an idea that you are doing a StrainLife, so it put in a StrainLife analysis glyph. You said you were doing we're doing a time series, so it puts a time series on there. So notice in the simulation input that it knows we already performed an analysis, and it read that in by the fact that it said one file is in there. If I hit the little display button, you see my model in there, and if I click the upper right maximize button, I can now see my model. At this point, just like in any type of code, any type of fine element code, you can go ahead and start manipulating. You can do things like zoom in, and you can go and fit to the screen. We can rotate the model and so on. In addition, if I right-click and hit Properties, the properties allow me to plot any of the results. So, for example, if I pull down the fact if I want to see, let's say for the bending load, what the stresses are, and I can select what stresses I want, let's say von Mises, I can click OK, and I can see what the results are just like we could in Workbench. And there are stress results for load step 1, which was our bending load. Just like any other type of code, you can go back to the display and change how you want it to look. For example, one thing that we often like to do is change the lines to show the mesh superimposed on the plot. So if I click OK there, you can see now what the mesh. Notice it's not a great mesh, but again, this is not a meshing webinar. It's a life prediction webinar. Finally, there are a few other things to note. One is groups. Any type of name selections or components that you create that exist in your model, you can bring those in. This is a nice way to limit where you want to perform a fatigue analysis on. So in this case, we're looking at the entire model. Okay, so at this point, we will minimize that, and now we have our model in with some unit loads. Now we want to define the time series loading. So what we're going to do here is we're going to go to File, Open Data Files, and we're going to go find a file that has our data for a bending and a torsion load that maybe we've instrumented this in a test and we know we know what that's going to define the cyclic loading. So I'm going to go up to the directory or browse to the directory that has a loading, and I'm going to, my loading happens to be in shaftloads.s3t file, so I'm going to add that to the file list. So notice when I found it and added it, it now appears here on the left side. This is all the available data that I can go around on my computer and find. And this S3T is just a common data file for containing loading. I'm going to drag it onto my time series input. Notice it says one test is now available, and if I click the display, you'll see that I have 2 loads on there, and let me maximize it. What you can see here is I have some test data of a cyclic vertical load, and in the blue down below, I have a cyclic torque load. And you can look at this data, and nCode actually has a lot of capability to edit this data and simplify it, take out portions maybe where we stop recording loads, and you can manipulate this data as much as possible. I'm just going to use it as is, so I will minimize that. Note that my finite element simulation is piped into strain life analysis. The time series loading is piped in, and this bill of materials is simply the material properties that I defined from nCode into Workbench. That was written here. So all 3 of those are fed into the strain life analysis. So at this point, I just have to set up, do the settings, do the load mapping, material mapping, and make sure that all the properties are set the way I want. So what I'm first going to do is right-click on strain life analysis and say Edit Material Mapping. It's going to say, do you want to run the flow up to this point so I know where everything is coming in? So we'll say yes, and let it just read all those things in. And what I'm going to do is, here is my material properties. I'm just going to drag those up. First, there's a different material in there from previously working on this model. So I'm just going to right-click and say Clear Material Assignment. And then here's the material I defined in the finite element analysis. I'm just going to drag that up and add that to Solid 1, which is the full model. And now I'm going to click OK. So all I've done here is Workbench knew that was the material I wanted to use. I just made sure that that was assigned to the material properties, to my model, the finite element model. Next, I want to edit the load mapping. I've already run the current flow up to here. I don't need to run it again. What you see here is we have the auto configure. By default, that's clicked on. And the way to look at this is up in the top left box here, I have the available load types, available finite element load cases. So load case 1 was our unit bending load. Load case 2 was our torsion load. Down at the bottom, I have the input from our time series glyph, and you can see there the red load is the vertical load, and the blue I showed you was torque. So nCode assumes right from the beginning, based on auto configure, that it's going to apply this red cyclic load to load step 1 and the second blue cyclic load to load step 2. And that is what we want, because that is vertical to vertical load and torque load to torque load. If I didn't want that and didn't want nCode to assume that, all I would do is click off auto configure. It will ungray all these things out, and then I can drag and drop and show which load goes with what load. In addition, you always have the ability to add dividers and scale factors to any load if you want to see the effect of that. In this case, everything looks good, and so I'm just going to click OK. Finally, I've already set up, because I went through Workbench, it knows the units I'm using, and we're going to use the rest of the defaults, and we're just going to run this analysis by clicking the little Run button up at the top. And this takes a little time, but not too long. And what you're going to see is, to the right, the 2 larger glyphs, which, of course, you can make these as large as you want by just, changing the size and moving them around. But in this flow, up on the top right is the fatigue results display. This will show contour plots of all of the fatigue analysis results, which mostly you're going to be looking at as either damage or life, which are the inverse of one another. Down below to the bottom right are just a numerical tabular form of essentially the same data. So first, let's maximize the fatigue results. And again, what is showing here is the damage. And you can clearly see that the combination of these loads, it's showing that in kind of this notch fillet region, that is going to be where the red is, and the maximum occurs at node 2445, and it looks like the maximum number of, or the maximum damage is 4.2 e to the minus 5. I'm going to right-click and go to Properties. Since we're really interested in life, I always like to look at life first to see how many cycles to failure. So if I change it to life and click OK, we get the same, obviously the same contour plot, and you'll see that the maximum or the minimum life is looks like it's about 24,000 cycles at node 2445. And again, you can do a number of things to find the maximum. For example, this little symbol here, if we click on that, we can get the node ID to be put on the plot. So if we're looking at node 2445, I can type in 2445 and say label, and notice it labeled it. And if I can, let's try to zoom in. You can see 2445 is as we expected, right in the reddest corner there. There's also the ability, what's called a hotspot detection, where you can ask for a hotspot list, and this will show you, if I widen up this, you'll see that there's a lot of information showing the damage values and the calculation method, the max and min stress and strain at this point, that it calculated the material property, and so on, so that you can look at the top life limiting points in your model. So for example, notice our node 2445 is the number one there. When I clicked on that, it automatically creates a line and highlights it to show where that is. If I click on any of these other points, it'll point to the regions in the model where these might occur. Most of these are falling off the plot area, but we could always zoom back out. And I'll just clear that feature label. Okay, so that gives us our results. Again, as I mentioned, the data value display is also available, and again, this gives all the information you would want for the life limiting points and locations in your model. And at the end here, you see the life, the number of repeats. Notice, by the way, when we're talking about repeats, this is like 24,000. That means that's 24 applications of this entire time series load. For this particular case, we're talking about that this full cyclic definition that we show here represents one full cycle of time series load. So it's saying that if this is what happens during a particular event for the shaft, that you would be able to, the fatigue life would end at 24,000. You would be at the point where that region in the notch would have reached its limit based on our analysis. There are many other things you can do with nCode, but that brings an end at least to what I wanted to show you here in this initial introductory demo of nCode. Again, it's extremely easy to use, but extremely powerful. There's many other issues and other features that are available, and hopefully we can bring you those in